All right, in this video, we're going to do two more questions off the review, the FRQ questions that mainly talk about area and volume of shapes. And so this one says functions f and g are given. F is the square root of x, so that is f. And then g is 6 minus x, so it's just linear. R is the region bounded by the x-axis and the graph of f and g as shown in the figure above. All right, so now we got an idea what's going on. Here's this region R. And we did this question on notes. We did the first part of this. Find the area of region R. So we're going to split this up, and we could do it a couple ways. We could split this up, and we could find this first part. This first region of R is the area bounded by the f function. And it's pretty simple. It's not area between two curves. It really is just the area from the integral from 0 to 4 of the f function, which I can just say f of x. I could also put in square root of x. Calculator's not allowed, so we'll have to do this by hand. So instead of square root of x, I'm going to go ahead and just write it as x to the 1/2 exponent, because I know I'll be reverse power ruling it here in a second. The second part of that area under the curve really is just a triangle. Now I could integrate this from 4 to 6 of the g function. And I'm going to do that just this time, even though we know the area bounded by that is just a triangle. It's just a triangle with a base of 2, a height of 2. So 2 times 2 is 4, divided by 2, so that's going to be 2. Right? No, wait. Oh, this is embarrassing. 2 times 2 is 4. Oh, yeah, half of that. So yeah, here's just 2. So we'll see that that's just 2 here in a few minutes. We're just going to make this more difficult. But really, you could just say this is just plus 2, and it makes it easier. But let's just see how that all works. So now we'll find the antiderivative of x to the 1/2, add 1 to the exponent, so it's 3 over 2, multiplied by the reciprocal of 3 over 2, which is 2/3. And we're going to evaluate that from 0 to 4. Then we're going to add the integral of this. So antiderivative of 6 would be 6x minus x squared to the 1/2, evaluated from 4 to 6. And that really is going to get kind of gross. So we should just know that is going to be 2, but just that this option exists. Okay, this is an FRQ question, so I can use safe stops, but this is not a safe stop yet. I have to plug in 4, so I have 2/3, 4 to the power 3 over 2, minus, now 0 to any exponent is just 0, so I don't have to put in that 0 part. And I could just say this is plus, and if I knew this was just 2 from a triangle, I could say that, and that is a safe stop. That is the area of region R. But if I didn't recognize that and I did this, I would say this is 6 times 6 minus half of 6 squared minus, plug in 4, 6 times 4 minus 1/2 of 4 squared. And this winds up just being 2, but that's good enough. That's a safe stop right there. Do not go any further. Just utilize the safe stop, be done. Use the time you'd be simplifying doing something else. But that's right. Even better, like even a faster way, if we'd have done this, if we said 2/3 of 4 to the power 3 over 2 is just 2, or plus 2. This is also equivalent, and we would have saved some time actually integrating that. So the fastest way you can do it that way. All right, part B. We did that before in the class, by the way. Okay, find region R. The region R is the base of the solid. For each y value, where y is in between 0 and 2, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose base lies in R, and whose height is 2 times y. Right, but do not evaluate the integral expression that gives the volume of the solid. All right, so the cross sections are perpendicular to the y-axis, so they're going this way. So if I want to find the volume is equal to the sum of an infinite number of areas, or just area. So to get the area, or to get the volume, I need the area. Every rectangle is length times width. So I need the length and the width. So, or the base and the height. So we'll say the base lies on R. So instead of length and width, we'll say base and height. So the base lies in R. So it's each one of those red ones. So even though, like, if I want to find the distance between two functions, I usually do top minus bottom. But this way we're going left and right, so I do right minus bottom. So the function on the right is g. So the base is equal to g of x minus f of x. And then the height is just 2 times y. So the tricky part about this one is everything needs to be in terms of y. So when I say g of x, it needs to be g of y actually, and then f of y. So let's find out what those are, and then we'll find out what the base is, or the base. So y, so g, where is it? G is equal to, so I'm gonna say y is equal to 6 minus x. Solve it for x, and I get y minus 6 is equal to negative x. X is equal to 6 minus y. And so that would be the base is 6 minus y minus, okay, the height would be, or the bottom function. So g of x minus f of x, y is equal to the square root of x. Square both sides, y squared is equal to x. So to find the base, the length of each red line segment, I do top function, which was g, in terms of y, minus bottom function, which was f, in terms of y. So the volume, now everything needs to be in terms of y because it's a dy. That means my limits of integration need to be in terms of y. So my cross sections start when y is 0, and they go all the way up to when y is 2. And then it's the area. I'm adding an infinite number of areas. So the base is 6 minus y squared times the height, which is 2y, dy. And that would be it. That would be the integral expression that would give the volume. Again, this is just the base. That's the height. And I'm adding up an infinite number of those areas for each cross section. The area of each cross section starts at 0 and ends at 2. All right, part C. There's a point P on the graph of f at which the line tangent to the graph of f is perpendicular to the graph of G. Find the coordinates of that point. So what this is saying, here is the G function. Okay, perpendicular means intersects at a right angle. So I'm going to do my best job. Okay, right angle. And what I want to do, don't take the whole thing. Let me see. Mess around for a second. Perpendicular, like that-ish? No. That looks pretty perpendicular. Okay, that blue line is perpendicular, we'll say. Now some tangent line on F, maybe right there, there's a point where it's tangent. And that point of tangency is the point that we're looking for. But there's that line it would be perpendicular to g of x, which is just linear. So we want to find that point P. Okay, so to be perpendicular lines have opposite, reciprocal, I don't know how to spell this out, I don't know how to spell reciprocal slopes. So if we gotta find the slope of G. The slope of G is just -1, so the opposite reciprocal will be 1 over 1, so just 1. So change the signs and flip the fraction, but okay, there it is. We flip the sign and we change the fraction. All right, so now we gotta find the slope of that. Where's the slope 1? And you're like, okay, slope. What does that have to do with anything? Remember, the derivative is the slope, right? So if I find where the derivative is equal to 1, I got to find that x where the derivative is equal to 1. Then I find the y that goes with that. So I got to find the derivative. F of x is equal to x to the 1/2 exponent. So f prime of x is equal to 1/2 x to the negative 1/2, subtract 1. This looks like 1 over 2 square root of x if I wrote it differently. Not sure that's really necessary. So I got to find the x. This is the derivative. Let's find the x. Or if I plug it into the derivative, that's supposed to be a highlighter. Let's find the x, or if I plug it in, that would equal 1. So multiply both sides by 2, 1 over square root of x. Okay, it would be better to have written this, kept it as an exponent. Would be 2. I guess I could do like cross product, whatever. But instead of this, actually do it from here. Yeah, that's good. Over 1 cross product. 2 square roots of x is equal to 1. I don't know what I'm doing right now. Divide by 2. Okay, this is working out. Square root of x is equal to 1/2. Square both sides, x is equal to 1/4. And that seems about right. Look at that. When we drew that, that looks like it'd be about 1/4. Find the coordinate of the point. So I have the x. To find the y, f of 1/4 is equal to the square root of 1/4. And that's technically right. So the coordinates points, I can say point P, just labeling what I have as 1/4, and then square root of 1/4, which is, that's 1/2, right? I could have left that square root 1/4. I should probably do that just to make sure we didn't make a mistake. Square root of 1/4. There we go. All right, that's it for that one. Okay, this one's calculator allowed. I did this before. I haven't looked at it in a minute. Okay, let R be the region in the first and second quadrants bounded above by this graph. So you could plug this into your calculator, get a picture of what it looks like. And below by the horizontal line y equals 2. Find the area of R. So I would go into Desmos and I would plug this in there. But I drew a sketch on this earlier. So my sketch, this is y equals 2. And then the other graph kind of looks like this. I don't need to know all those points, but I mean, it might be kind of good to know these points are 3, 2, and negative 3, 2. Find the area bounded by, above by that curve, and below by y equals 2. So that region right there. And that's supposed to be look more symmetrical. Find the area of that region. Okay. Area is equal to the integral from negative 3 to 3. I'm adding up all these distances. The distance from top curve to bottom curve is always top curve minus bottom curve. If I add up an infinite number of those lengths, it gives me an area. So top curve is 20 over 1 plus x squared minus 2 dx. When I plug this into my calculator, put parentheses on the whole thing, I get 37.9618, and there might be another number here. I didn't write it down. I should have, but just plug it into your Desmos on your own, make sure you get it, and then write the correct number. Decimal spot, then 5 numbers. Okay. So I want to say, you make sure you put this, and you put the number that the calculator tells you. And it doesn't hurt to write area. But since it told you, like, to find the area, I mean, it knows. They know. All right, find the volume generated when R is rotated around the x-axis. So again, if you're watching this over the little snow break, we haven't done washer method yet. The washer method is used when you're trying to find the volume of a solid formed. Okay, this does not work. Okay, we should just do, okay. Never mind, it's all here. It's that part. Looks like the bumblebee part. So that bumblebee part, if that is rotated around an axis, but that region is not butted right up against your axis of revolution, then it's going to be a washer method. So we're basically finding the area of a big circle, and we call that radius big R, and you're going to take away the the hole. So this is called little r. Little r. Why did I draw big R? Little r. That's called the washer method. That would find the area of each little circle with a little hole in it, add up an infinite number of those, it gives me the volume. So my big R is going to be distance from axis of revolution, which is just the x-axis, all the way to the end of the function. So just function value. So I could write big R is equal to 20 minus 1 plus x squared. Little r is always going to be 2. It's the distance from axis of revolution to that first part where your shaded region starts. Okay, so if I'm setting up and find the volume, I need the area of the big rectangle or the big circle, which is pi times r squared, big R squared, and the area of the little one is pi times little r squared. So I could write my volume as this. It'd be -3 to 3. I could say pi times the big radius, which is 20 minus 1 plus x squared, dx. And then I could say minus, so that'd be this the whole volume. And we're basically subtracting the volume of this cylinder in between, because there was a void there. That'd be -3 to 3 pi times little r squared, 2 squared, which is before, dx. So I could, this would be one way to set it up. Some people always do it this way. Some people put the pi's out in front, but other than that, it's the same. I like to do it as one big one. So I put the pi on the outside, -3 to 3, 20 over 1 plus x squared minus 4. That's in parentheses dx. That would give me the same thing. That's just how I see it. But you do it the way that you see it. Oh, this is actually all wrong. Oh my goodness. All right, so those have to be squareds. So if you're making a comment in the comments, then like if you're doing this on part B, trying to figure out what I did wrong, just remember the squares there. No, not the square there, still wrong. I squared the 2, but I didn't square the other radius. So this is still wrong. Dang it. This is embarrassing, but y'all are used to it by now. There we go. If you're someone who's watching this video for some reason who's not one of my students, yeah, I'm just kind of slow. Now you know. Anyways, part C. Oh, the number. Yeah, really slow. Is 1871.1901. All right, last one for this video. Thank goodness. The region R is the base of the solid. For the solid, the cross-sections perpendicular are semicircles. Find the volume of the solid. Okay, so I need the volume is equal to the integral from some number to some number, and it's going to be an infinite number of semicircles. So 1/2 pi times the radius squared. And it'd be in terms of x. Because they're perpendicular to the x-axis. So cross-sections go from the x-axis, they're perpendicular. So they start at this number and they end at this number. Now, where would they start? So they start at -3 and the cross-sections end at +3. I could put this 1/2 pi, I could put that in front, just to be fancy. It's calculator active anyway. But we need the radius. So the radius of each semicircle, so coming out of here, what color have I not used? Green. So there's semicircles. So there's the base of the semicircle and it's coming out. So the radius is just, too many colors, it's just half of that, right? Radius of each semicircle will be half. So distance from top curve to bottom curve is 20 over 1 minus x squared minus 2. And I want half of that. So I'll multiply by half. All of that is the radius of each semicircle. So that's what I would be integrating, and I need more space. So the radius, I already forgot what it was. 1/2 of that that's the whole radius, square that, dx. So you plug that into your calculator, but they want to see that written on your paper, so they know you know what you're doing. So the answer is 174.2684, some other number. Make sure you write the 5th decimal. All right, the next videos will be particle motion. That's like the second part of, or the other half of Unit 8. And thank you for watching. Hopefully this helped. And again, just really proud of y'all. Keep working really hard. Bye.